All right, let's get started. This is the first of two pre-recorded lectures that we're going to be doing as we begin our discussion on beam deflections. So just a little bit of background. So right now we should have finished our discussion on shear and moment diagrams. Homework 5.6 is due today when this video goes live, which is on October 15th. And homework 5.7 is due on the 18th. Since I'm pre-recording this, I'm not sure where we are on the homework grading, but the homeworks 5.4 to 5.5 should be in the process of being graded. Hopefully they're graded by the time this video goes live, and the solutions are available on Blackboard. So today what we're going to do is begin our discussion on deflection, and the topic is really covering deflections of beams and frames because the mechanics are the same. They're both looking at flexural deformations. I will warn you there is a little bit of calculus coming in this video, but in order to set the stage, I feel that what we ought to do is go back and see if we remember how we compute truss deflections, because we're going to compute deflections utilizing the same approach. So let's go back to truss displacement. So if you remember, if we have a truss, remember when we handled trusses, the first thing that we did was we learned how to analyze the truss using the method of joints and method of sections, and then we learned how to compute the displacements, and we looked at the displacements on a joint by joint basis. And so to compute the displacements, this was the formula that we used. We ended up summing the little f's times the big F's times the L's divided by the EA's. The big F's are the internal member forces from the real loads on the structure. Remember, the real loads being the original loads that were on the truss, and then the little f's are the internal member forces from the virtual loads. Remember, they were unitless, and they came from placing a single load at the truss. What we did is we placed a single load at the joint of interest. It had a magnitude of 1, and we placed it in the assumed direction of the displacement. And remember, if we got a negative, let's say we're looking at vertical deflection and we placed a downward load and we got a negative answer, that just means that our assumption was incorrect and it's actually deflecting upwards. So that was a pretty straightforward thing to recognize. Now, another thing that was worth mentioning is the length of the member, and it needed to be expressed in inches. So one way of thinking about this, and this will become clear later on in this lecture, is that in order to use the method of virtual work, if we're using conventional units, then we basically employed a unit conversion factor of 12. So we could take our raw data, our members, lengths, and feet, and our member forces and kips, et cetera, and we could just multiply everything by 12, and that would have worked as well. And I mentioned that because we're going to have a similar unit conversion factor for beam deflections later on. And finally, we needed the modulus of elasticity of each member in KSI, and then the cross-sectional area of each member in square inches. So beyond the two results of the structural analysis, we needed the length of each member, and then we needed the properties related to the member's constitutive behavior. It's material parameters, and then it's section property. And so those two quantities are going to have a parallel in beam deflections as well. Now, what we were doing when we did this, by summing up these little f's times big F's times L's over EA's, what we were doing was basically summing the energy in the structure. So remember, these were the two graphs that we generated looking at the energy component for trusses. And so we had the external work done and the stored strain energy, and the idea was to set those two terms equal to one another and solve for the displacement. And if you remember, when we set this up, what we were really after was this term right here, because when we were initially discussing the energy, we found that one of the problems with energy methods was that we couldn't, we could not solve for the displacement at a given joint if there wasn't a load there. So remember, we placed a preload, a fictitious load, a virtual load at the joint of interest so that we could track the energy at the joint that we're interested in. And so ultimately what we were after was this delta 2. And so we ended up breaking this up into a series of energy components, and what we were originally recognizing was that W2 and U2, we could set those two equal to one another, and they would be the most advantageous for solving the deflection. So we would set this equal to that, and that's where the little f big F times L over EAs came from. And as for the unit load, well, we just set the P1, the fake virtual load, equal to 1, and then 1 times delta equals that, and since delta 2 is what we were after, it's pretty straightforward. Now, I do want to make a note before we begin on constant versus variable forces, because this is kind of important. So remember, again, what we're doing is we're summing the U2 terms in each member. So you can see it's right here that when we solve for the deflection, we're summing the U2s, which is basically just, that formula right there. But we're doing a sum of these constant terms. Little f times big F times L divided by EA. Those are constants, right? That definition only works if the little f and the big F are constant along each member. Now for trusses, that makes sense. If you have a truss, here's a truss, and here's just a very, very simple truss, and I put, a load right here. Let's say this member experiences 100 kips in compression. Well, it's the same 100 kips in compression everywhere along the member. So it's 100 kips in compression here and here and here and here. It's the same compressive force everywhere along the length of the member. The thing is, with beams, that isn't the case, okay? And so it's worth mentioning what would happen if the loads were variable. Let's see what would happen if the loads were variable. Well, if the loads were variable, what we would have to do is break out integration. Remember, definite integrals are really just sums, right? We're just summing those differential elements along the along a given region. So if the loads were variable, what we would do is sum up the displacements along each little incremental element. So the idea is that we would take our expressions of equilibrium, Hooke's law, and compatibility. So equilibrium says that the stress is F over A, but in this case, F is a function, right? It's variable, so it might not be a constant value. We still have Hooke's law, stress is E times the strain. And then for the strain term, instead of just saying delta over L, we're saying a little increment of displacement over a little incremental element. So it's the derivative of displacement with respect to x. And so we could plug these two terms here. This could become the F over A. This could become the derivative of displacement with respect to x. And then we solve for d delta, and we get this. So this is just me taking this equation and rearranging it and solving for d delta. Well, if we do that, what do we got? Ooh, that's a little bit of a typo. That needs to be A. All right. So we'll fix that. Okay, so then what we would do is say, well, we're summing up the DU2s. I remember the DU2s was the fake load times the real displacement, right? So fake load times real displacement, okay? And then integrate, right? And so the big thing I want to illustrate here is, and this is something to keep in mind whenever you are assessing things in engineering in general, is typically when we start out in engineering, we try and keep things as simple as possible to come up with a usable solution. And then what we might do later is say, well, what if this changed? What if that changed? Well, the idea is that our resulting solution might be a little bit more complex, but if we reverted back to those original assumptions, we should still get the same answer. So I propose that this expression right here would be the expression that you utilize if you had variable loads. But what happens if you have constant loads? Does this still work? Well, let's see. All right, if these terms are constant, little f, big F over EA, if they're constants, then I can factor them out. Then I have the integral of 0 to L, and all I have inside is just dx. And if you remember, the integral of dx is just x. So I have little f, big F over EA, and that's x evaluated from 0 to L. And so what happens? You plug in the top number minus, you plug in the bottom number, and you get little f, big F over EA times L minus 0, or that right there. So you still get the same expression if those terms end up being constant, but if they are variable, this might be a little bit more usable. And I only mention that because we are going to see some variable loads here in a bit, and we are going to have to integrate. So it's good to sort of get into that frame of mind. And yeah, that's a typo. That's supposed to be F over A there. I will fix that in the upload. Okay, so now let's talk about deflections and beams. So ultimately what we need to do is derive a differential equation for beam deflection, okay? And to begin this discussion, I want to start with some math preliminaries. And we're going to start real basic just to make sure that we're all on the same page. So we're going to start with the area under a curve. So, and the reason that we're starting with the area under a curve because I want to go back to this concept of section properties. So what I mean by a section property is if I have some shape, some bounded region, what are some numerical properties that define that region, such as the cross-sectional area, the location of the centroid, the moment of inertia. If you look at the handout that I gave you in lecture 15 on the analysis project related to the W12 sections, that's what that handout was from the steel manual. It was just a list of all the section properties that characterize, certain eye shapes. And those numerical properties are what we use to classify their resulting behavior. So we start off with basic. So we have a function f of x, and I want to determine the area between 2 points A and B, and we can define that pretty easily as the integral, right? The integral from x equals A to x equals B of some function is the area. And so something that you might see me do later on is instead of writing all of this, I might just write it like that. I might say the integral over the region of dA. The idea is that I'm summing up these little dA elements along the region. That's just sort of a shorthand way of writing it, so I don't have to write all of this hullabaloo with every problem. And using this notation, what we can do now is define what are called moments of this area, okay? So the idea for the moment of the area is if the area is the integral of just dA, the first moment of area might be the integral of x dA or the integral of y dA, okay? Those would be what we call moments of area. And one of the things you'll notice is that the symbols are flipped. So for instance, qx is the integral of y dA. That is not a typo because, for example, if this is your x-axis and this is your y-axis, and I have some region here, right? How far, let's just use the centroid as an example, how far is that from the x-axis? Well, that distance is y, right? That's how far you are from the x-axis. That's why the symbols are flipped. So the first moment of area with respect to x is the integral of y dA, and the first moment of area with respect to y is the integral of x dA. And what we can do with these expressions, these are useful because they help us determine the location of the centroids, okay? Because if we take the integral of y dA divided by the integral of dA, that tells us y bar. If the integral of x dA divided by the integral of dA is x bar. So that's where those come into play. The second moment of area would be the integral of, let's say, y squared dA, or the integral of x squared dA. And second moments of area, we tend to have a special name for those. We call those the area moment of inertia. And as you're going to see here in a bit, they are very, very prevalent in beam theory in determining the behavior of elements under bending. Now, just to be clear, we could come up with third moments, fourth moments, fifth moments. We could go crazy with this. But really, these are the only two that we find readily useful in engineering, at least for most applications. So finally, what I want to talk about with preliminaries is this term curvature, and I'm using a specific term for that. So let's just go back to basics. So let's say I have a function f of x, okay? We can compute the following. First off, we can compute the slope of that function at any point, and that's pretty easy. We use the derivative. We take the derivative of f of x, and that will tell us the slope of that function at any given point. That's what the first derivative tells us. If we take the second derivative will tell us the concavity of that function with respect to x. So this is stuff that you probably remember from your Calculus 1 courses. But what you might not remember is how to compute the curvature of a function. The formula is this. It's kind of bloated. I guarantee you if you still have your calculus textbooks, go open them and you'll find this in there. This is the definition of the curvature of a function. And it's possible that this might have been skipped over or at a minimum covered very lightly, but I just wanted to show you that this is the mathematical definition for the curvature of a function. What we're going to do later on is we're going to just say that this equals the second derivative. And the reason that we're going to do that is because when we deal with beams that are undergoing small deformations, we're going to say that the first derivative is small. And so if you take that number and you square it, it gets really small. So we're going to take this term here and say it goes to 0. And so 1 plus 0 raised to any power is just this over 1, which is just the second derivative. Now this is the curvature of a function. The radius of curvature would just be the inverse of this. So if kappa, this letter kappa is the curvature 1 over rho, or rho is 1 over kappa. Kappa being the curvature, rho being the radius of curvature. So these are some mathematical definitions that we're going to use later in our derivation. So let's get into this derivation. So unlike the mechanics for axially loaded members, which were pretty straightforward, the mechanics for beams and frames are a little different when we're talking about flexure. But I should mention our assumptions are largely identical. So the first is that the behavior is linear and elastic. So we're going to assume that the beam sort of behaves like the rubber band, like the truss member did. So the idea is if you take the member and apply load, it deforms. But if you take that load off, it reverts back to its original shape, and that ratio is linear. Okay, so linear meaning that there's a constant proportionality between the applied load and the resulting deformations, and then the elastic behavior means when you let it go, it reverts back to its original shape. So we're not going to consider any permanent deformations, which is quite common in structural analysis applications. And the other thing is that the deflections are small when compared to the original member lengths. So the idea is that if here's my beam, we don't really have beams in structures that bend like this. I mean, we don't. Here's this building, and it's not like the load on the floor above us is causing the beam to bend like this. It is deforming, but not very much, very, very, very small. So that we don't have to go back to recompute reactions or reassess the equilibrium based on how the structure looks like once it's deformed, okay? We call that a first order analysis. So second order analysis is if we do have to consider the deformed shape, which we do have to do this sometimes whenever we're looking at stability, like columns and buckling and things like that. Okay, so if we look at the deflected portion, and I'm going to switch to my my webcam here so that you can kind of see my beam a little bit better if I can find my mouse clicker there. Okay, so here's this this beam element here, and so what we're going to do is we're going to take this element and we're going to deform it. Okay, now if you look here, you're going to see three lines going this way. Okay, let's take a look at this one here in the middle. If we take this beam and we deform it, let's see, do it like that. The idea is that the line that's going down the middle is not changing in length. So whatever the length was before, this is the same length. But the idea is that the lines above this, like this line right here, the idea is that it's getting shorter. The idea is that not this line, but this line right here, that this line is getting longer. So that the idea is that central line, what we call the neutral axis, it is not changing in length, but the lines above it are getting shorter and the lines below it are getting longer. Okay, so if we go back to the lecture here, so here's an image of what I'm talking about here, and let me change my color here so we can kind of see what I'm talking about here. So the idea is that this line right here does not change length after the beam is deformed. Okay, so what I want to know is I want to see if I can determine the length of that line. Well, this goes back to a pretty basic geometry, right? If this right here is the radius and this right here is the angle, if you take the radius times the angle measured in radians, that will tell you what the length of that line is. So we're going to call that L initial, okay? L initial being the initial length of the beam before it deforms. And we can use this because we're assuming that solid line remains unstretched. But for all of the other lines, like for example this this dashed line right here, let's take a look at this dashed line, it does change length, okay? So what is its length? Well, it's the radius in this case, rho minus however far we are from the centroid times that angle. So now we have an initial length, and now we have a final length. Okay, so the final length is rho minus y times theta, or rho theta minus y theta. Okay, so what we're going to do is go back to our fundamental definition of strain, and we say, well, what is the definition of strain? It's the change in length divided by the original length. So the original length goes on the bottom, and what goes on the top is the change in length. Final minus initial. That'll tell us the change in length. So we go through and we chug it out, and we get rho theta minus y theta minus rho theta. So the rho thetas cancel. And then we have negative y theta over rho theta. So we get this. So the strain is negative y over rho. And then if stress is E times the strain, then we get this. Something we can actually use in our next slide. Okay? So I'm actually going to rewrite this up here. So sigma equals negative EY over rho. Just going to write this up here so that we have it in the top of our heads. Okay, so that's looking at the stress from a compatibility standpoint. Now let's look at it from an equilibrium standpoint. We can also look at this from a moment standpoint by integrating the stress along the cross section, right? So the idea is that each element, so let's just make this like a rectangular section, right? Let's just keep it like this. So this is a rectangular beam. Let's say this is the neutral axis. And so if I'm looking at, let's say, this element, I propose that the area of that element is some differential dA, some little incremental area, multiplied by the stress. That will give us the force in that element. And then the moment arm, y, is how far it is away from the centroid, right? So if we take the force, multiply it by the moment arm, that will tell us the moment in that differential segment, right? So the idea is like dm is sigma y dA. And then all we have to do is integrate that to get the moment, okay? Now, the only thing that changes from here is I've got this little negative term here. The negative term just comes from the sign convention that we use in civil engineering, where we use like smiley face positive. That's where that negative term comes from. But we could leave it out. It won't really change the be all end all final answer. It's just it's what we tend to use. Now, what's valuable here is now we have this expression for moment. What I'm going to do is this term stress, I'm going to plug in that right there. I'm going to plug in negative EY over rho. So using our previously defined term, we get this. So I plug in, instead of where it says sigma, I say negative EY over rho. The negatives cancel. And then what I do is I take the constant terms, pull it out, and I get this. Okay. Now, is there something there that is familiar? There should be. That should be somewhat familiar. That is, oh, hold on, my mouse pointer went away. That's the moment of inertia, that integral of y squared dA, right? So the integral of y squared dA, what I can do is I can replace this and come up with that. So now I have what this term, or this equation, m equals EI over rho, and we're really starting to get somewhere with this. We have a name for this. We call it the moment curvature relationship, because m equals EI over rho. Remember, rho was that term radius of curvature. Let's go back to that term curvature. So we can rewrite our expression a little bit. So we have m equals EI over rho. Let's rewrite that using this curvature expression. So curvature is m over EI. And if you recall, this was the expression that we used for curvature, but we're going to take that displacement with respect to, we're going to take that first derivative with respect to displacement squared. We're going to take that term, set it equal to 0, so that we basically can say that the curvature and the concavity are basically the same thing, since the deflections are very, very small. And we come up with this. This is arguably one of the most fundamental equations in all of mechanics, the idea that the second derivative of deflection is m over EI. And we're going to use this expression to develop our method of virtual work. Now, one of the things I'll mention when we get into this is that we're using virtual work in this course to compute deflections. There are other ways to compute the deformations in beams, and your book is littered with other approaches. For example, there's approaches that are called geometric methods, and geometric methods are all about trying to come up with solutions to this differential equation. Some of them are just directly solving the differential equation. We call that direct integration. Some of them are using the geometry of the solution, for example, the conjugate beam method, in order to assess the deflection at a given point. But the reason why I like to use virtual work is we can use the same concept and the same approach that we used for trusses, the real load and the virtual load, and then plugging it into a simple to remember expression. We can use that same approach and it will work for any beam subjected to any loading. It also, and this will become clear near the end of our discussion of deflections, is it's a lot easier to assess the deformations due to other types of mechanics, such as shear deformations or axial deformations or so on and so forth. So we're going to use virtual work. So first off, I showed you earlier how virtual work applies to trusses. We have the real load and the virtual load. So how does virtual work change for beams? Well, recall that when we did virtual work, we analyzed two structures. We had the original structure with all the loads present, and then the virtual structure. The virtual structure was we took all the loads off and we put a single load at a point of interest. So what do we do for beams? Well, for the external work, we're going to do basically the same thing. If we're interested in computing displacement, we place a unit load at the point of interest. And if we're interested in determining slope or rotation, we place a unit moment at the point of interest. So to go back to the webcam, let me find my mouse pointer here. So to go back to the webcam, here's the beam. And if the beam is deforming, there's more than one thing happening, right? Okay, let's see. Not only is the beam actually displacing up and down, so like here's what the beam was before, and then it deforms, so it's actually changing it's translating up and down, but it's also rotating, right? So here's the beam flat, and then here's the beam deformed. It's actually there's elements of the beam that are actually changing in rotation. So not only do we want to know the how much the beam translates, but we also want to know how much the beam rotates at times. So if we're interested in translation, we place a unit load. If we're interested in slope or rotation, we place a unit moment at the point of interest. So just so you're aware right off the bat, I'm going to use the terms slope and rotation interchangeably because not only does your textbook, but other textbooks can sometimes use those terms interchangeably. So if I'm saying slope or rotation, it means the same thing. The same thing with displacement or translation or deflection. They all basically mean the same thing. And just like with truss deflections, we assume a direction for the displacement or the rotation. And if our assumption is correct, then the answer will be positive. So that's the same too. So in order to find U2, this is what changes a little bit. And this goes back to my original discussion about constant versus variable loads. So if we go back to the differential equations, so the second derivative of deflection is m over EI. And so I'm introducing something right here that the slope or the rotation is just the derivative of the deflection, right? Which that makes sense, right? If I have a function for the deflection, the slope is just the first derivative. So the second derivative of deflection is the first derivative of slope. What we're going to do is we're going to integrate this because the moment changes as a function of x. And this is really, really important. And this is why beams are different, right? If I have a beam, right, this is not an unheard of moment diagram, right? That's not constant as a function of x. It's changing all over the place, right? So if the moment is changing as a function of x, we need to be able to account for that when we sum up our energy, because that's what we're trying to do when we use the method of virtual work, is we're trying to sum up the energy inside the system. So what we're going to do is we're going to look at basically how much each element deforms. In this case, because we're looking at moments, we're looking at how much each element rotates. So we're looking at the little incremental rotation in each element and then integrating to sum up the energy. So d theta is m over EI dx. In this case, m might be a function. It might not be a constant value. It might be a function. And so U2 is going to be d theta times that virtual load. So now you're noticing some new notation. Instead of big F's and little f's, I've got big M's and little m's, real moments and virtual moments. And then just integrate U2 so to get U2. So integral of little m big M over EI dx. So set the two energy terms equal. External work done equals stored strain energy. Remember, 1 times delta equals all that hullabaloo. And boom, there's the deflection. So that's how we determine, in general, deflections in beams, is we use the principle of virtual work, and it's really not all that different, right? With trusses, it was little f, big F, L over EA, and we were summing that. Now what we're doing is summing little m, big M over EI, but we got to integrate it first, then sum it. And the reason we have to integrate it first is, again, because the moment. Now, so in order to compute the deflection, we need a couple of things. So the first thing we need is an M of X. We need a real moment function resulting from the original loads on the beam, and then likewise we need a virtual moment function. And again, virtual moments come from placing a single load on the beam at the point of interest, magnitude of 1, in the assumed direction. Okay, we need our modulus of elasticity, and we need the moment of inertia. And again, moment of inertia, it's different than with trusses. We needed the cross-sectional area because the mechanics were different. We were looking at sigma equals P over A for truss members. Okay, now one thing before we discuss sort of a glaring problem we need to solve on this slide is that more often than not, well, sometimes we have moment diagrams that can be defined by a single moment function, and sometimes we have moment diagrams that can be defined by that need to be defined by multiple moment functions. And if we need to define multiple functions to define the moment diagram, then we have multiple integrals to evaluate. So if you remember in the schedule that I discussed, we have one day devoted to single moment function problems and then another day devoted to multiple moment function problems. So we're going to take that aspect of it and take our time with it, because I don't want that part to be complicated. Now, that's basically it in terms of the theory. There is one thing left that we need to discuss, and those are units, okay? Because if you notice, these are foot kips, but this is in KSI, and this is in inches to the fourth, and that creates a glaring unit inconsistency. Well, we need to consider our dimensional issues here, and I'm sure that some of you are thinking about, well, you know, wouldn't it be a lot easier to operate in SI? It might be, but you still have dimensional considerations that you need to take into account. For instance, you might reference your member lengths in meters, but you might reference your cross-sectional properties in millimeters or centimeters. So even though you are using a unit system that's built on factors of 10, there are still dimensional considerations that you have to take into account, and there's still a dimensional consistency that you need to be aware of, even in SI. So this consideration would be there as well. But what I want to do is derive some USCS conversion factors. If you remember, for trusses, there was a conversion factor. The conversion factor was 12. Okay, so we have a conversion factor that we need, or two conversion factors, I should say, one for displacements and one for rotations, that we need to derive for USCS. So before we jump into some examples, which is what I'm going to do in the next lecture we're going to look at a single moment function problem, and then we'll look at a multiple moment function problem. But before we jump into examples, let's look at how the units play out. Okay, so we're going to start with the second derivative of deflection. So the second derivative of deflection is M over EI. Okay, now I want you to think about this from a units perspective. Okay, and it's all we're doing. We're doing just a dimensional analysis here. Okay, so think about this in terms of polynomials. If I have a polynomial, let's say it's, you know, x squared plus 4x plus 3 or something, but the highest term is x squared. When I integrate that, it goes up in order, right? The highest term will be x cubed, right? So whatever the polynomial is, the highest term, if you integrate it, you get one more higher, right? Well, I propose that if you, from a units perspective, kind of the same thing happens, okay? The functions are with respect to x being along the beam. So if I integrate this term, if I integrate the second derivative and I get the first derivative, from a units perspective, that answer is going to have one more unit in terms of the length. So this is M over EI, and I'm saying this is ML over EI. I'm not saying that's like the answer. I'm not saying whenever you integrate that you get ML over EI, because it would depend on what the function is. I'm saying from a units perspective, there's one more L term to consider, and so if you integrate it again, you're going to have yet one more L term, okay? And so I'm using this to develop some conversion factors that we need to use later, okay? So let's talk about the units that we typically use in USCS units in structural analysis. So we typically refer to our forces in kips, and we tend to refer to our member lengths in feet. And so that leads to, for example, distributed loads or triangular loads being referenced in like kips per foot, and moments being in foot kips, but it all kind of comes from kips and feet. But for the moduli of elasticity, we tend to use KSI, and for moments of inertia, we tend to use inches to the fourth. Okay, well, if we go back to this, let's go to ML over EI. Let's just look at the rotations, right? So if I plug in foot kips for moments, I plug in feet for lengths, I plug in KSI for E, and I plug in inches to the fourth for I, and I chug this out. On the top, I'm going to have kips and then feet squared, and on the bottom, I'm going to have kips, and then I'm going to have inches squared, right? Because these two are going to cancel and be left with inches squared. So I'm left with something that's not really all that usable, right? I'm left with feet squared over inches squared. If I want the rotation, that doesn't make sense to express rotations in feet squared per inches squared. It's not usable, okay? Same thing with deflections, right? If you do the deflections, instead of getting feet squared per inches squared, you get feet cubed per inches squared. And again, that's not usable. So as you can see, there's a problem that we have to address to ensure that the answers make sense, that they're usable. And again, we had a unit conversion factor for trusses. Our conversion factor was 12 because we had to convert the member length to inches. So I want to see if we can develop a conversion factor for beam deflections or beam deformations. So we need conversion factors, okay? So maybe the first thing we ought to ask is, what are our desired units? Like, what do we actually want the units to be at the end of the day? So for slopes and rotations, now there's actually a little bit of there's differences in the school of thought on this. Some folks think that displacements and rotations should be, that slopes and rotations should be in radians. I don't. I tend to think that slopes and rotations should be in degrees, because when you actually look at some of the problems that we assess, the radian values can be really, really tiny. So I think that by converting to degrees, it makes it a little bit more digestible. And you don't have as many trailing decimal values to deal with. It's pretty compact in terms of collecting the data. For displacements, deflections, how much the beam is actually deflecting up and down, I think it would make sense that we would want this in inches. Okay, so if you remember our let's take the rotations. We got feet squared per inches squared. Okay, so what we might want to do is convert that feet to inches, so maybe 12 inches to 1 foot. And so that cancels one of these, but then we have to do it again, right? To cancel the other foot. So now we have inches squared over inches squared, and now if all we did was stop right there, that would give us radians, right? But I want degrees, and so there's 180 degrees in pi radian. So if I take this and multiply it by 180, that'll give me my conversion. So for slopes and rotations, here's what I propose that we do. We take what would have been our answer, and we multiply it by 12 inches per foot, and we do that twice because we've got feet squared here, okay? And then we take that resulting value and multiply it by 180 over pi. And by doing that, our final answer will be in a unit of degrees, okay? For displacements, we don't have to do the 180 over pi, but we have to use the 12 inches over foot, but we got to use it 3 times, okay? 3 times because we have a foot to the third power that we need to get rid of. So 12 times 12 times 12. So For slopes, we had 12 times 12, which is 144, but for displacements, we have 12 times 12, which is 144 times another 12. And if you take 144 times 12, you get 1728. So I propose that our conversion factors are for slopes, 144 times 180 over pi, and for displacements, it's 1728, okay? And what this will allow us to do is use conventional units, and then we just do the problem and multiply it by this at the end of the day, and it gives us our answer. I know that this lecture, and that's actually it for the lecture. I know that we've gone through a lot of stuff, a lot of data, if you will. But the big thing I want you to recognize is that we now have a simple formula, the integral of little m big M over EI dx, where we have these unit conversion factors. We're actually not doing any problems on this lecture because we're going to utilize this in lecture 24. So what we'll do is we'll take it one step at a time, do a simple problem, and then ratchet it up a little bit in difficulty. All right. And we've only been recording for about 40 minutes, so I'm letting you off a little bit early. That's all I have in this video. And again, in the next video, we'll start using this. So I will see you all when we return.